Morning. This is the math department at Amjad High School for grade 11. This is our second video on probability. Exercise 1. A class consists of 30 students, 14 like volleyball and 18 like basketball. 6 students like both sports at the same time. As you can remember, such problems last year were modeled by a Venn diagram. So the set of volleyball students is this set consisting of two parts. 8, these 8 like only volleyball. These 6 not only like volleyball, but they also like basketball. But when I say students liking volleyball, I'm talking about all of the set consisting of 14 students. Verify that y is 4. Do not forget here that the total number of students is 30. So simply y is 30 minus these. So y is 30 minus brackets 8 plus 6 plus 12, which means that y is 4. Now the experiment is that one student is chosen at random. Calculate the probability of each of the following events. The students like volleyball. I'm not saying likes only volleyball. I'm saying likes volleyball. So volleyball, the set of volleyball students is all of this shaded set here. So these are 14 students, 14 over 30, and that's 7 over 15. What's the probability that the student likes basketball? Basketball is this set. All of the set, not only the 12. These 12 like only basketball, but I'm not saying the student likes only basketball. I'm saying that the students like basketball and likes basketball, and consequently the student can be any one of these 18 out of 30, which is a 3 out of 5. Now, what's the probability that the student likes only basketball? So this is the set, or this is the part where students like only basketball. Actually, it means in symbols, the probability that the student is liking basketball and not volleyball, which is 12 over 30, which is 2 over 5. Now, what's the probability that the student likes basketball and volleyball? So be careful here to the word and. As we said, this is the intersection. It's here, the overlapping region between the two sets, consisting of 6 students, so 6 out of 30, and that's 1 over 5. Now, what's the probability that the student doesn't like any of the two sports? Actually, doesn't like any of the two sports is the region here, which is outside this cloud. So it's the shaded region where 4 students are there. So the probability that the student doesn't like basketball and at the same time doesn't like volleyball, and these are 4 students, 4 over 30, 2 over 15. By the way, there is another method here. Whenever you have probability of events such these events, you can interpret the meaning of the event as we did here and count the number of students satisfying this set, or you can use formulas. For example, you know that probability of B bar intersection V bar using De Morgan's theorem. It's B bar intersection V bar is B union V all bar. And the probability of whatever bar, which means the complement, is 1 minus that. And the union is nothing but this white region here that represents the union. And the union can be seen as another formula, like probability of B minus probability of V minus probability of B intersection V, which is this one, which is the same answer, 2 over 15. So whenever you solve a problem in probability, you have 2 options. Either satisfy interpreting the meaning of the event, then calculating the accepted cases, or shifting to using formulas. For sure, in such a situation, it will be much easier to interpret the meaning because it's very clear the number of students, and actually you are drawing only one name. You are selecting one name, and the chart here using Venn diagram is extremely clear. Now, what is the probability that the student likes only one sport? The region in Venn diagram, or the regions in Venn diagram where the students like exactly one sport will be these 8 and those 12. So these 6 should not be accepted because these 6 like 2 sports at the same time, and I want exactly one sport. So that's basketball but not volleyball, or volleyball but not basketball, and it's clear again on Venn diagram. You don't need, by the way, to write this notation. You can go directly to the answer, which is 12 over 30 plus 8 over 30, which is 20 over 30, which is 2/3. Find the probability that the student likes at least one of the 2 sports. As you can remember, the expression at least is used to mean or, the mathematical or in probability, or the union of the 2 sets. And the union is this whole set. So actually we're talking about those students, if I want to interpret, I'm talking about those students who like only one sport plus those who like 2 sports at the same time. So it's 8 plus 12, which is 20, and those 6, it's 26 over 30, which is 13 over 5. Or probability that the student likes at least one of the 2 sports means 1 minus the probability of the complementary of that event, which is the probability that the student doesn't like any of the 2 sports, which means it's 1 minus 4 over 30, which is again 13 over 15. Or, since you can interpret at least as a union, and since you're talking about probability of B union V, you can see the union here is very clear on Venn diagram. But be careful in some other exercises. You may not have the Venn diagram. So you cannot look at the Venn diagram. So it could be better to do method 2 or method 1. It depends on the situation. In this situation, I prefer this last method because at least means union. And the union is this big cloud here, the 2 sets together, which is clearly 26 over 30. Exercise 2. A and B are 2 events of a sample space omega such that the probability of A is 0.2, probability of B is 0.5, and the probability of A bar intersection B bar is 0.7. Calculate the probability of A intersection B. Here you must shift to the use of formulas. First, we have probability of A bar intersection B bar is, using De Morgan's theorem, the probability of A union B all bar, which is 1 minus probability of A union B. But this is given 0.7. So equating 0.7 to that, you can get probability of A union B to be 0.3. Now shifting to the basic formula in this chapter, we have probability of A union B is probability of A plus probability of B minus the probability of the intersection. Plugging in the values, and you will get probability of A intersection B 0.4. Exercise 3. An urn contains 15 balls. These balls are classified per color, red, yellow, and blue, and per number. Each ball carries a number, either 1 or 2. There are 5 red, 6 blue, 4 yellow. How many numbered 1? 6. How many numbered 2? 9. Distributed according to these colors and numbers. One ball is drawn at random. So the experiment here is one ball is drawn at random. Consider the following events. The selected ball is red. B, the selected ball is blue. A, the selected ball is numbered 1. So here you can see the balls, their colors, and their numbers. Calculate the probability that the selected ball is red. Simply, there are 5 accepted balls out of 15. That's 1/3. Find the probability that the ball carries the number 2. Simply, you can count them. These are 3 plus 4 plus 2. So there are 9 such balls. So 9 over 15, 3 over 5. Calculate the probability that the selected ball is red and carries the number 1. So you can search about the balls satisfying these two conditions at the same time. These 3 balls are okay because they are red and carrying the number 1. So actually in symbols it's intersection. And the interpretation of intersection here is very easy. So 3 over 15, which is 1 over 5. The selected ball is not yellow and carries the number 2. So the ball must be not yellow, which means it has to be red or blue, and it must be carrying the number 2. The balls are very clear. There are 6 such balls. 6 over 15, which is 2 over 5. Now, what's the probability that the selected ball is blue or carries the number 1? Again, whenever you have the expression containing or, you have either the choice of interpreting the meaning of this event, but you have to know how to interpret the or. So, or means union. So all the balls, whenever I read the selected ball is blue, this means that all the blue balls are accepted regardless of the second part of the statement, because you have an or here. So if the ball is satisfying at least one of these two, it will be accepted. So since the ball is blue or, this means all the blue balls are okay. Carrying the number 1, this means all the balls carrying number 1 are okay. So you can count all the blue balls and all the balls carrying number 1. But be careful here not to count the same balls twice. For example, these 2 balls may be counted when you are counting the blue balls, but you may count them again when you are counting the balls carrying the number 1. You shouldn't do that. So I advise whenever you have an or, if you see that it's confusing, it's better to use a formula. So since or means union, so you can say B union 1, which means formula, probability of blue plus probability of carrying number 1 minus the probability of blue and carrying number 1. Now the interpretation of each of these 3 events is easy. You can avoid confusion, but if you can count, you can give the answer directly as 10 over 15. This will be accepted. We're not forcing you to use this formula. Now, B is the event the selected ball is blue. Calculate the probability of B bar, which means the ball is not blue. The ball is not blue means it can be red or yellow. Simply, you can count and you can find the blue are 5. The yellow balls are 4, so you have 9 such balls. There is another method here. You can count the blue balls, and B bar will be nothing but 1 minus probability of B. So B bar is the complementary event of B. So you can count or calculate the probability of B, then you can do 1 minus that. It's up to you. In this case, both are easy actually. Let R be the event the selected ball is red. A, the selected ball is numbered 1. The question here, calculate the probability of A bar intersection R bar, which means the ball is not numbered 1. In this context, this means that the ball is carrying the number 2. R bar means the ball is not red. Again, since you have A bar intersection R bar, these combined events, you have 2 options. Either using appropriate formulas or interpreting the meaning of this. By the way, whenever you have intersection in such problems, intersection is easy to be interpreted. So what are the balls which are not red and carrying number 2? It's easy. These balls are carrying number 2 and they are not red. And these 3 balls here. So simply you can count the balls. But some students may use formulas. It's up to you, by the way. Don't forget here, in this context, A bar means the ball is not numbered 1, which means it's numbered 2. So A bar intersection R bar means carrying number 2 and not red. Count these as I did. That's 7 over 15. Some students may use the Morgan's theorem. But I think in this problem, it's like this. I advise whenever you have a probability situation, you try to interpret the meaning of the event. If you think that interpreting the meaning of the event is confusing, shift to formulas. For example, in this part, calculate the probability of B bar union A. Let me try to interpret the meaning of this. This means that the ball is not red or carrying the number 1. Again, I advise, since you have a union here, which means or, which means at least, especially you have at least with a bar like a conjugate, not. I think that some students may try to count, but it will be confusing to them. I advise in the case of the union to apply a formula. So this will be probability of this plus probability of that minus probability of this and that. I think this is much easier and not confusing to students. So not blue is clear. Carrying number 1, simply count them. 3 plus 2 plus 1, 6. Finally, not blue and carrying number 1, that's easy. Not blue and carrying number 1, this ball here, and these 3 balls here. So these are 4. So the answer is 11 over 15. Thank you for this session for today.